Hey class, it's Mr. Wolfe here. Sorry I can't be in class today. I'm feeling a little bit under the weather, so I'm actually filming this at 7:50 a.m. Because I wanted to make sure that you just weren't given the key, but some explanation about how to go through these gene expression scenarios. Because I understand that we've done some, but you also haven't had a whole lot of feedback yet. So hopefully this is helpful feedback. What I'm literally, it's kind of a janky method. I'm just going to be pressing Command Y to kind of go in reverse on how I completed the key here. So this is the scenario, a time to divide and not divide, right? And the first thing is let's just like set up our key. All right, so if my gene is repressed, it's red, activated green. And then what I'm going to do is I'm going to start to read my scenario, right? The intestine cells undergo mitosis more than once a day. Pancreas cells, however, can go weeks before dividing. All right, so I want to develop a model to show the difference between intestinal cells and pancreas cells. Right. The first thing I want to do is what's the gene, like we're gonna model all the genes in the scenario, but what gene's important to the scenario? Notice that it's talking about dividing. So I'm going to look at my gene expression model reference sheet, and the gene that's involved in cell division is my cell growth controller gene right here. So I know that this is going to be not actin. The cell growth controller gene is going to be the one that I care about. All right, so once we get here, that's what we really want to be focusing on, but I want to make sure that I'm modeling all these other genes too. So let's go ahead and do that. All right. For actin, notice that I just put this this X here. That means that the gene's turned off. It's still there, but it's just not being read ever. How do I know this? Because it says actin, so I'm going to go to my reference sheet right here, and it looks like actin is only in muscle cells, and this is an intestine cell, and this is a pancreas cell. So that means in both of these, it's going to be turned off. All right, the cellular respiration enzyme, that's in all cells except red blood cells, and this is an intestine cell or a pancreas cell, so I automatically know that my cellular respiration enzyme is going to be turned on. That kind of makes sense because all cells need to do cellular respiration for energy. All right. So then I'm going to look for lactase, and lactase is that enzyme that helps you to digest milk, and it's in your small intestine cells. So I'm gonna activate that gene. It should be red. All right. And then for my pancreas cell, notice this is a different type of cell, and if it's only in my intestine cell, it's not going to be in my pancreas cell. So it's going to be turned off in a pancreas cell. All right, so now we're finally getting to the protein that we care about here, the cell growth controller, right? Where my intestine cells are dividing a lot and my pancreas cells are dividing a little. This is a really tough gene because the cell growth controller, it stops cells from dividing and helps prevent certain cancers, but when it's on, it stops cells from dividing. So if my intestine cell is dividing a lot, it actually means that my protein should be repressed, where it's just not being read at the moment. Right? The example I gave in class is like me leaving the classroom and one of you throws a paper ball at one of your classmates because I'm not there. When this protein's not there anymore, the cell's going to be like, all right, let's just start dividing. All right. The pancreas cell, all right, now it's not dividing, which means that the cell growth controller is on. This protein's being made, and it's saying to the pancreas cell, hey, we should not be dividing right now. All right? And really, that's the big difference between these two different cells. This is why, even though they have the same DNA, this is why intestinal cells divide so much more, is because their cell growth controller gene is repressed a decent amount of the time. All right, so let's go on, and I'm going to look at my hemoglobin protein. All right. Hopefully you guys kind of start to not memorize, but maybe memorize or start to get the hang of like which proteins are in which cell. But hemoglobin is only in red blood cells, so it's going to be turned off in my intestine and pancreas cells. All right. Insulin, all right, is only in my pancreas cells, so it's going to be turned off in my intestinal lining. But if it's in my pancreas cells, that means that I should actually be turning it on for my pancreas cell right here because it's making that protein. All right. Now, as for the fat enzyme protein and the DNA repair protein, notice that if they're in all cells, right? And if the scenario doesn't give us anything about if the DNA repair would change or the fat breakdown enzyme would change, if they're on in all cells, we could always assume that these genes are active. You always need to break down fat. You always need to repair your DNA. Again, you could be given some scenario where these are repressed or turned off, but for the most part, at least in this one, where really the only thing that's changing is the cell growth controller gene, that's it. All right, so what I'm going to do now is we've modeled everything, but we do need to answer a few questions first. So what happens to the gene in the cell and the intestinal lining of the cell? It's referring to the cell growth controller. Well, we just modeled this, that it is repressed, right? It's red right here. And then what happens in the pancreas cell, that's this question right here, well, that gene is activated, all right? So the last thing we need to do is, okay, if it's activated or repressed or whatever it is, how does that impact the function of that cell? So I said something along the lines of, all right, so by repressing, oh, it all came up at once. So by repressing the gene, the cell growth controller protein does not get made. So here I'm not making that protein. And without this protein, the intestine cells will divide. So notice like the last thing that I say here is kind of linked up to what's happening in my scenario, the fact that intestinal cells divide frequently. All right? So that's it for my model. Let's go on to the next one. All right, this one's bro, do you even lift? So let's just get our key down first. All right. And then I'm going to read my scenario. And it says that if you're doing like this HIIT workout, your muscle cells continue to do a high amount of cellular respiration in order to do mitosis to repair damaged tissue and prepare cells for the next exercise. Okay. So, sorry about this, guys. All right. So as I read this up here, it talks about that my cells need to do more cellular respiration. So my gene of interest, if I look at all these genes right here, my gene of interest that's involved in cellular respiration is going to be my cellular respiration enzyme right here. So that's my gene of interest. And now I'm just going to start to kind of model what's going on here. All right. So now I'm going to focus on actin, and actin is in muscle cells. All right, right here, right? Actin's in muscle cells. So I'm going to have that activated in the gym rat. All right. For the couch potato, I'm going to have it activated as well. All right. Now, what you could have done is, I'm going to go back really quickly. Notice that our gene of interest here is the cellular respiration enzyme right here. But technically, if you made the actin more activated, I would be okay with that because technically the cell's probably making a little bit more actin. Right. But since actin's not the focus of this, I'm allowing some leeway between these genes. Right? So you'll notice that there is some leeway between some of these genes if they're not the main gene that we're focusing on. All right, so the cellular respiration gene, that's always turned on in cells unless they're red blood cells. Right? Cellular respiration enzyme right here if we look at our sheet. Lactase is only in intestine cells, and I'm dealing with muscle cells, so I know that that gene is going to be turned off. Oh, sorry. Wow, I completely skipped this. Sorry. So our cellular respiration enzyme is our gene of interest. So what's the difference between the gym rat and the couch potato? Well, they're both going to be activated, but the gym rat is going to be doing way more cellular respiration. Again, how do I know this? The caption will tell you, right? These muscle cells do a high amount of cellular respiration if you're doing these HIIT exercises. All right. So then we'll go on, and like I said, lactase is only in intestine cells, so it's going to be turned off in muscle cells. All right. And then if I go to my cell growth controller, right, there's multiple things you could have done here. You could have said, you know, it doesn't seem like my muscle cells are being turned on, so I'm just gonna, or my muscle cells are dividing, so I'm just gonna have this turned on. However, notice that it does say that in order to do mitosis to repair damaged tissue, so it's very possible, and to tell you the truth, if I were modeling this, right, I would actually make this repressed. All right. Now, again, you might be wondering, like, wait, which one is it? And again, the focus of this model is on the cellular respiration enzyme. So these are the enzymes I care about, the genes that I care about the most. So there is some leeway here. I would make this repressed, just so you guys know, but you could have easily turned it on as well. Right, now, for the couch potato, their cells are probably not doing a whole lot of mitosis, which means that cell growth controller gene is going to be turned on. All right, so then for hemoglobin, that's in the red blood cells, so that's turned off. All right, insulin, and again, I'm getting all this information from my sheet right here. Insulin is only in my pancreas cells, so that's turned off. All right. And then, just like I said before, the fat breakdown enzyme and the DNA repair protein. They're in all cells, and unless it says otherwise, we always need these genes turned on to just kind of help do normal cell functions. Right? So here's my model. Now I need to just make sure that I kind of wrap it up by answering some of these questions. So what happens in the gene to this gene, the cellular respiration enzyme in the gym rat? Well, it's activated, but specifically, well, actually both. So I just got to go and do this in the right order. So both are activated, right? But the cellular respiration enzyme is activated a lot. So that's the big difference here. All right. So how's that going to affect my cell? Well, when the actin gene is activated a lot, it will make, oh boy, I said actin. When the cell, I need to change this. All right. So when the cellular respiration gene is activated a lot, it will make more of the cellular respiration enzyme. All right. And then, all right, with more of this protein, the cells can do more cell respiration to repair or to recover after exercise. All right, something like that. All right. And again, the big difference is the cellular respiration enzyme for the couch potato and the gym rat, but you probably could have also had the cell growth controller turned off as well, because we'd be doing a lot of mitosis. It wouldn't be necessarily a make or break, but I think the most accurate thing would be to have it turned off. All right. Thank you for watching and kind of dealing with this this janky kind of just Microsoft Word explanation. Have a good day, guys.